Today, we know the topography of Mars 100 times better than the topography of our own oceans. This is because more than 2/3 of our planet is covered by deep oceans. What would the Earth look like if we could drain the oceans? Well, you would probably ask for a window seat on your next flight to Hawaii, and let me show you why. So far, only a few percent of the oceans have been surveyed by ships. Shipboard surveys provide very high spatial resolution, but these ships travel at only about 12 miles per hour. It's been estimated that 125 to 200 ship years of survey time will be needed to map the deep oceans, and this would cost a few $billion. Fortunately, such a major mapping is largely unnecessary because the ocean surface has broad bumps and dips which mimic the topography of the ocean floor. The extra gravitational attraction of these features on the seafloor produce minor variations in the pull of gravity that produce tiny variations in ocean surface height. These bumps and dips can be mapped using a very accurate radar altimeter mounted on a satellite. Most of the new information comes from the CryoSat-2 satellite, launched by the European Space Agency in 2010. While the primary mission of the CryoSat-2 is to monitor the volume of ice in the polar regions, the satellite continues to collect data over the global ocean. The CryoSat-2 data are more accurate and provide vastly improved coverage than the data from all previous satellite altimeter gravity missions. We will now fly along the global mid-ocean system. The red line marks the location of the spreading boundaries. These images show the vertical gravity gradient, which highlights the smallest scale features on the seafloor. We start at the mid-Atlantic ridge. The seafloor spreading boundary consists of north-south oriented spreading ridges connected by east-west trending transform faults. The new gravity model highlights these features in unprecedented detail. As we cross the equator, one can track the fracture zones from South America across the mid-Atlantic ridge to the coast of Africa. Close to the continents, the original seafloor is buried by thick layers of sediment, so the match points where the continents rifted have only been seen in these new gravity data. It is in these sediment-covered areas where most of the new discoveries are being made. Flying further along the southern mid-Atlantic ridge, the orthogonal pattern of ridges and transform faults is very clear. There is also a less distinct north-south corrugated pattern associated with the abyssal hills that are formed parallel to all the spreading ridges. Most of these abyssal hills are uncharted by ships, so we are seeing them for the first time in this gravity data. In the far South Atlantic, we fly over the Bouvet Triple Junction, defining a connection point between three major tectonic plates. We continue along the slow-spreading southwest Indian Ridge axis. The gravity anomalies from the north-south trending fracture zones are very strong along this ridge. Next, we approach the Indian Ocean Triple Junction, which marks the connection point between the African plate on the left, the Indo-Australian plate on the right, and the Antarctic plate below. We continue our flight along the southeast Indian Ridge. This is one of the most remote areas on our planet and includes the region where the Malaysian flight MH370 disappeared. Note that the spacings between these fracture zones increase along this section of the ridge, and the location of the spreading axis is less pronounced, and there are fewer earthquakes. This dramatic change in the style of seafloor spreading is due to an increase in the spreading rate above a threshold value of 70 millimeters per year, or about 3 inches per year. As we fly from the southern Indian Ocean into the South Pacific Ocean, we begin to follow the Pacific-Antarctic Ridge. From this point until we reach the end of this ridge axis in the Gulf of California, the transform faults are infrequent and the ridge axis is a narrow high. This part of the South Pacific Ocean has some areas the size of the state of New Jersey that have not been surveyed by any ship. We continue our journey up the Pacific-Antarctic Rise to the Chile Triple Junction and then over the Eastern Microplate. This section of the East Pacific Rise has the highest spreading rate on Earth of 120 millimeters per year. Finally, we continue across the Galapagos Triple Junction and up into the Gulf of California. At this point, the global spreading center goes on to land, where it is called the San Andreas Fault System.